Swayam Prabha. Digital India. Educated India.
Hello, welcome to the course on transport phenomena. So today this is the lecture 17, and so we are going to talk about transient heat conduction. Okay, so far before this we looked at heat transfer through extended surfaces, uh, their effectiveness and efficiency and all those things. So in this one we'll start the transient heat conduction that will include the time effect. So far we had looked at steady state, so this lecture is on transient state, transient heat conduction. So we'll incorporate the effect of time. Okay. Okay. So today we'll first see some description of transient conduction. Then we are going to talk about two methods, and they depend on the kind of situations you have. So first one is lumped capacitance method, which is a relatively simpler way to analyze transient heat transfer, but you cannot use it always. And this is related to thermally thin body. We'll define what thermally thin body is. And then we'll see what is known as spatial effect. So we'll talk about the so here in this part we'll mostly talk about temperature as function of time. Here we will talk about temperature as a function of x and time. We are going to look at only 1D transient condition. So and we'll just discuss about the plane wall. Okay. So there could be two situations. In one case, we'll see where you don't have any temperature gradient within the wall. So it may be initially at some temperature Ti, and then you submerge it into some fluid that is at some temperature T infinity, and then we analyze how the temperature of this entire body will change. So we don't have any temperature gradient within the body. In this case, we'll see that initially again you have a body which is at temperature Ti, which is everywhere you have Ti, but then we'll look about how will the temperature change with respect to time when you submerge this into a fluid which is at T infinite temperature. Okay. So we are going to discuss about these two cases, and our focus will be on analytical solutions. We are not going to look at numerical solutions. Okay. So an example of what we are just talking about, the change in the temperature of the body. So let us say you have a hot forging, which is initially at high temperature. So it could be a steel forging, let's say, that you use crankshaft for your automobile, or maybe large forgings. The shape is in this case, the shape does not matter a lot, because what we say is when we submerge this high temperature hot solid in a liquid, or it could be in a gas, then so for all time less than equal to 0, you have T equals Ti, and just at T, or you can say at T equals 0, you submerge it. So then the temperature of the body will change with respect to time. Okay, so intuitively you can think that initially it is at some temperature, and then it will probably change. So, but in this case, what we are saying is that temperature, this is temperature versus time. So initially can be at 1,000 Kelvin, and then if you keep it at very long time, it will keep decreasing, and it will come to some T infinity, right? So in between you will have some temperature, and you want to know what is the functional form of this temperature variation with respect to time. Okay. So we would like to know how long would it take to reach to T infinity, or some other things, like it can be, start with 1,000 Kelvin. How long does it take to reach it to 800 Kelvin, and 600 Kelvin, and 400 Kelvin, and so on. Okay. And how much energy it will lose with time, so that you can know the change in water temperature as well. You don't want water to boil. Okay. So we make an assumption that there is no temperature gradient in the solid. So let us say that for whatever region we'll discuss when that is possible, when it is not possible. So we say that there is no temperature gradient in the solid. So there is no, so in within the solid, the entire solid is at some temperature T, which is function of time. Since there is no temperature gradient in the solid, we cannot use heat equation. Our heat equation essentially depends on the temperature gradient, spatial gradient of temperature. So we have to go back to energy balance. So whatever the energy is getting out, there is some stored energy, MCP delta T, MCPT, and so on. So whatever the stored energy, change in stored energy has to be the energy, thermal energy being taken out due to convection, right? So the heat transfer between this solid and this liquid is due to convection. So if we do this, then the change in stored energy essentially has to be QQ convection. Okay. So E in there is no input heat in the body. It's all, everything is going out. E in minus E out, so is equal to stored energy, and E out is essentially H8 HAS T minus T infinity. Okay. Yeah. So AS is the surface area of this body, and T is any T is the function of time, and minus T infinity is the temperature of the liquid, which again we have assumed constant with time. It may be large volume of liquid, so that its temperature does not change appreciably. And that should be equal to the change in stored energy with respect to time. So rho Vc, C is the heat capacity, V is your volume, rho is the density of solid. So rho Vc dt by dt. Okay, so we can write in dt by dt because temperature is only function of time, not function of space. So we can write ordinary in the form of ordinary differential equation rather than partial differential equation. So once you do that, what you have done is you have set it up as first order linear differential equation. So that is pretty easy to solve. So we just to simplify it further, we substitute, we define a variable called theta, which essentially gives you the temperature at any time minus T infinity. So you can write theta I as Ti minus T infinity, where your Ti is initial temperature of the solid. Right. Okay. So when you substitute this theta here, you have minus HAS theta. This is theta. Rho Vc, and you can see that since our theta is T minus T infinity, dt by dt is going to be equal to. So if you differentiate on both sides with respect to time, you can write d theta by dt is equal to dt. Okay, so that you can, so from here you can replace d theta by dt. So now you just do variable separation, and so you have d theta by theta, and then you have rho Vc by HAS. So that is now simple. It will give you an exponential decay, right, as expected. So theta by theta I is a function of this exponential minus T by this thing, rho Vc by HAS. So this is exponential decay, which is very similar to what you see in capacitors. So if you have a charged capacitor, how does the voltage decay with respect to time? It's essentially the same thing. And this is this kind of behavior you can see in other kind of decays as well. Okay. So in this case, the time constant tau is essentially, tau is equal to this denominator here, 1 by HAS times rho Vc. So if you look at this is essentially, what does this give? This gives you the convection thermal resistance here, right? So this term gives you this term gives you the convection thermal resistance. So this is the convection thermal resistance, and then this is the rho Vc is essentially capacity of that solid to keep the heat. Okay. So this you can see that tau is again RC, which is similar when you have the capacitive discharge. RC is your time constant. Okay. So this is your thermal capacitance. This is your convection resistance. So what we have come up with is very simple, way to analyze the transient heat conduction problem, provided we can make an assumption that the temperature does not depend on space, x. Temperature does not depend on x, it only depends on time. Within the body, the temperature is uniform. Okay. So if you look at this thing, if you want to plot, it has to be an exponential decay. So at time equals 0, this thing is 1. So initially you have some theta I, right? And as you go, so at t equals infinity, this will become 0. So it will become, at t equals infinity, this term will be 0. Okay. So what does this theta 0 means? Theta is defined as t at any time temperature of the body at any time t minus t infinity. So if this is 0, that would mean that t at that time is equal to t infinity. So it will take very long time to reach it exactly infinity. But as you know, this exponential decay. So the decay is actually quite fast initially. Okay. So you can see that it has also dependence on RC. So the time constant, as your time constant increases, your cooling rate will become slow and slow. Okay. So just from this you can know. So if you increase, for example, heat transfer coefficient, then you are increasing this thing, so your time constant decreases, so your cooling is faster. This is as expected, right? Similarly, if your body can, if your density, heat capacity, etc. are higher, then it can retain heat for longer. So your capacity is increased. So this thing will move here. So it will be difficult to. Okay. So the other thing that we want to know under these conditions is how much heat has transferred, because maybe we want to know how typically in such cooling system you have the tank that you are forging and then quenching it. So you will have some inlet here and some outlet here, so that you maintain water temperature at infinity, right? If you keep cooling a lot of hot objects in this, the temperature will rise. So you want to know what should be your circulation rate. So you want to know typically Q, that will give you an idea of what should be your circulation rate, that you can get just from Q. Okay. That Q is equal to any times HAS your theta. But you may also want to know how much cooling has happened. So how much heat is being extracted. That also you should know. So to know that, what you can do is essentially heat transfer rate times dt integration will give you the total energy that is being transferred. Okay. So this is equal to HAS theta dt, and theta we know from there that this is HAS, you can leave here. This will be theta I, from here we know. Theta I exponential minus t by tau. Exponential minus t by tau, where tau is again constant for a given system. Theta is constant. So we can take HAS theta I and then 0 to t exponential minus t by tau dt. Okay. So this we can again write HAS theta I. The integration of that will be exponential minus t by tau and divided by minus 1 by tau, right? So this will be minus 1 by tau, and then you do 0 to t. Okay. So if you do all these things correctly, HAS tau theta I, there is a minus sign here. And then if you substitute t, it will be like that, and then it will be this thing. And when you substitute 0 here, it will be 1. So you will have this thing minus 1, or if you remove this sign, it will be 1 minus exp minus t by tau. Okay. So this is how your heat transfer, total heat that is being extracted will change with respect to time. Okay. So once you substitute the equation for tau is your from here, tau is this thing 1 by HAS rho Vc. So HAS will cancel out, So you will have rho Vc theta I. Okay, so this gives you the change in total energy that is being transferred with respect to time. Okay, so this is what we call as lumped capacitance method. And in summary, we have these things. Theta is theta equal theta I exponential minus t by tau. Then you have the energy that is being transferred that you can calculate from there. And so now we need to see that we have done the analysis, but we don't know when it will be valid. Okay. So we need to see how when it will be valid. So to do that, let us start with we are looking at the validity of heat capacitance method. We'll start with steady state conduction. We'll discuss later how it's related to transient. Through a plane wall where you have fixed temperature Ts1 and Ts2, and here you have some convection. So you have conduction heat here, heat rate, and you have convection. So at the wall, if you do what you call surface energy balance, then you will have Ka by L, Ts1 minus Ts2. Negative sign is incorporated here. Ha Ts2 minus T infinity. Okay. So this is conduction, this is convection, and if you rearrange it, you can write Ts1 minus Ts2 divided by Ts2 minus T infinity is equal to this by this. So this you can write 1 by Ha. So that's 1 by Ha part is in denominator, and then you can write L by Ka. L by Ka will just go here in the numerator. So what you see is this is your conduction resistance, this is your convection resistance. So the temperature gradient, the physical significance of this term over here is that the numerator actually shows what is your temperature gradient within the body in comparison to what is your temperature gradient, temperature difference at the surface to ambient atmosphere. Okay, so our situation is, our previous analysis will be valid if Ts1 minus Ts2 is very small, or this ratio is very small. The temperature difference within the body is much smaller than compared to what is the difference outside. Similar assumptions we can recall we did in thin problem as well. So Ts1 minus Ts2 is very small, if we can say, or other way around, what we can say is if your conduction resistance, conduction thermal resistance is much smaller, so you have a very conductive, thermally conductive body, then compared to what is the convection resistance, then we can say that our analysis will be valid. So if you just rearrange all these things here, this equation will give you HL by K, which we call it as Biot's number. Okay, which is very important in heat transfer. So this is the Biot number. If what we say Biot number is very small, then our heat capacitance method should be valid. Okay, so just recall that this K is the thermal conductivity of solid, which comes in from here. So that is how you should calculate the Biot number. Okay, you should not calculate from K of fluid outside. Okay. So this is what we are saying, that if your Biot number is smaller, and as you can see in this here, temperature profile with respect to Biot number. So if Biot number is much less than 1, then the temperature gradient within the body is much smaller. So this is your plane wall, and you have some both sides you have some T infinity. So convection is happening both sides. Initially you are everywhere at temperature Ti, but with respect to time, when you quench it, or when you bring it to this atmosphere, it will start cooling off. But this is the direction in which time increases. So as you increase the time, it will cool off. So the temperature will reduce from Ti to this temperature to this and this. But if your Biot number is much less than 1, then it will decrease in a fashion where your internal temperature gradient is very small. Right? If Bio is equal to 1 and Bio is greater than 1, then you will see that the internal gradient is much larger. In this case, you can say that the gradient may be almost similar, internal and external, but here your internal gradient is much larger, because your Biot number is it's greater than 1. So if this is the case, then we call this thermally thin, because because there's no, there is no temperature gradient within the body. So we can call it thermally thin. And for this part, your lumped capacitance method is valid, and we take this number as bio is less than 0.1. Okay. So to define the Biot number, we saw that bio is your HL by K. So for there could be cases where your L, your geometry may not be. It could be cylinder, it could be sphere, or it could be some non-regular geometry. So for that, what we define is called characteristic length, and characteristic length is defined as volume of the object by surface area. And physically, you can see this is meaningful in the sense that surface area is responsible for convection, and this is responsible for how much heat it can conduct, it can store. So V by AS is your characteristic length. For plane wall, you can see this. You can do the analysis to show that actually the LC will be equal to L, not 2L. So if your plane wall is of thickness 2L, if you do this V by AS, you will see that your LC is equal to L, not 2L, and physically it makes sense, because your temperature, the temperature distribution within the wall is actually symmetrical about this axis, because condition in both sides are same. So from so the for cylinder, if you do the calculation, you will see R0 by 2, and for spheres it's R0 by 3. Let's skip that. Then we'll further analyze this aspect, RC part of this. So we have seen that theta is equal to theta I exponential of this. So now if you look at this RC part, HS by T, HST by rho VC, we can simplify it, because we have said that V by AS, V by LC is equal to V by AS. So this is H times V by AS is LC rho C. Okay. So now we know that the bio number is. So if you try to get the bio number out from this one separate, and then we see what is left over. So HL by C, HLC by K, this is your bio number. Then what you have left is you have to multiply by K here. T is already there. Rho C is already there, but you have one LC is here, and then you have multiplied one LC on the numerator. So you have to multiply again. So that is LC squared. So this you have bio times alpha T by LC squared. So this is now a new dimensionless number, what we call as Fourier's number. Okay, Fourier number is essentially it is dimensionless time. Okay, so and K by rho C is your alpha. We have seen it before. Alpha is K by rho C. So K is your thermal conductivity, and rho is density, and C is heat capacity of solids, and this is your thermal diffusivity. This essentially is measure of how fast heat can diffuse in a solid. Okay, so now we can write based on this analysis, we can write theta is equal to theta I, that is exponential minus Biot number and Fourier number. Okay, so in general, for the calculation, what you need to do is you need to first start any such problems. You have to first calculate the Biot number, where Biot number is H, LC, where LC is characteristic length, by K, where K is thermal conductivity of your solid. You first calculate. If you see that the Biot number is less than 0.1, then you can use lumped capacitance. Okay, only if this is use lumped capacitance. Use lumped capacitance method. So that means that you can use this equation. And now to use this equation, you first see what you need to calculate. Do you need to calculate the time required? So from this equation, you can calculate either the time required to reach certain temperature, or you can also calculate temperature at certain time. Same thing, temperature at at certain times. If someone asks you that so initial temperature is 1000 Kelvin, how long will it take to reach to 700 Kelvin, you can calculate it. Or what will be the temperature after 2 hours, you can calculate it. Okay, so you see what you need to calculate. Accordingly, you need to calculate the Fourier number. Either you will know in the second temperature at certain time. In this case, you will know the Fourier number. Either you will know the Fourier number or you have to calculate the Fourier number. That is the question. Okay, so if you know Fourier number, then you can calculate theta, or if you know theta, you can calculate the Fourier number. So either one of two type of problem. Okay, so you have to first do this thing and then check. Okay, so we'll end this part of the discussion on with these two practice problems. So you have to calculate the Biot number for cooling of this 50 mm thick aluminum plate, which is initially at 700 Kelvin, and it is quenched in oil that is at 300 Kelvin, close to room temperature. And for this quenching, the heat transfer coefficient, convection heat transfer coefficient is given, and you are given thermal conductivity of aluminum and thermal conductivity of oil. So what you have to do is you have to first calculate the in question 1, you have to calculate Biot number. So you know Biot number is HLC by K. So you have to first calculate what will be LC, and then you know H and K. You have to be careful which thermal conductivity to use. Okay, and then you can solve it. The second is related to the first problem, what we just discussed. You have to find how long would it take for the plate to cool to 450 Kelvin. So you know theta is equal to theta I exponential minus bio Fourier. This is valid only if bio is less than 0.1. So you have to verify from first calculate and verify that this is true. If this is true, then you can use this equation. If this is not true, then probably you have to look at the next part of the lecture and then solve it. So you know theta I, and you also know theta because t minus t infinity you know, and t also you know from here. So from this equation you can calculate, you know, Biot number, and then you can calculate the Fourier number. This is what you need to calculate. Once you know Fourier number, from there you can calculate alpha t by LC square. So from there you can calculate, you know, alpha t by LC square. So Fourier numbers, from there you can calculate the time. Okay, so you can spend few minutes solving these two problems. Okay, so after doing this question, let us now we'll look at the spatial effect. So far we had only looked at the temporal aspect of transient conduction. So temporal aspect is what makes it transient, right? So we looked at you know, we have a it could be any arbitrary shape so far, but from here we'll look at the spatial aspect, and you know, general heat diffusion equation is in 3D. So this should be your y squared, and this would be your z squared. Sorry. So earlier also, I think one of the earlier lecture I used the same equation. So it should be del 2t by del x squared plus del 2t by del y squared plus del 2t by del z squared. So this is of course in 3D, and then you have the transient part here. So if you want to include the spatial effect, you need to solve this this differential equation, which is both which will give you the t x y z in the space and then time. But the analytical solution of such 3D equations are not possible. So we look at you know, let us look at only the 1D problem, and we'll see how to you know, how to solve this equation and come up with an analytical solution that we can use to determine t as a function of now x and time, right? So spatial and temporal. So we start by considering standard 1D geometry for our discussion. So mid plane is x equals 0, this side is x equals minus L, and this side is x equals L. Okay, so you can see that this is a symmetric you know, so it will be a symmetric condition. So initially, we again say that we'll look at some, you need boundary conditions to find the solution of this equation. So you will need one boundary condition or initial condition, so to say, in time. So that is Tx0 is equal to Ti. So at the beginning, you have the temperature everywhere is Ti. Then we'll need two in space. So the first one is kind of because of symmetry. What happens is initially you have this plate of some thickness 2L initially at temperature Ti, and now you are dipping in some cold fluid or exposing to cold gas. Okay, so you either dip in cold liquid or you expose to cold gas. But what is important is both sides will see the same condition. So initially, if it was at temperature Ti, there will be change in temperature and it will cool down. So, but that change, will now be, it has to be symmetric with respect to x equals 0. We are no longer restricting ourselves to thermally thin body where we had a Biot number less than 1, so specifically 0.1. So for those cases, the temperature profile was within the body was not appreciable. So you could just consider that at any time T, entire body was at some temperature time T, right? So in this case, we are saying that no, that is not a requirement anymore. So we can find general solution. However, because of the symmetric nature of the problem, you will see that about this point, you will have symmetric temperature profile, because if you are sitting here, you will see the same condition this side and this side. So heat transfer rate has to be the same. Okay. The second, so this is your, if you recall from your boundary conditions, this is the second type of boundary condition, which is constant flux, but we are saying adiabatic in this case. So this part, it's adiabatic. No, if you there's the situation, both sides are same here, so your profile will be symmetric. Okay. The second one is is related to surface conditions. So on these surfaces here or here, across this surface, the heat transfer due to conduction should be equal to heat transfer due to convection. Okay, so this is your third type boundary condition. Okay, so theoretically we should be able to now solve it and find our temperature distribution with respect to x and time. Okay, so if you just take all the variables that temperature depends on from this slide, it's x, alpha, time, L, T infinity, Ti. So if you see it, temperature will depend on all of these variables and H. Okay. So what we'll do is we'll start by non-dimensionalizing the equation, so that non-dimensionalization has many benefits. First of all, our idea is essentially to first it's partial differential equation, and then T has so many linked variables here. So we would try to non-dimensionalize and reduce the number of variables. Okay. So we define theta star. Theta star is defined as theta by theta I. We already saw theta is T minus T infinity. So theta I is Ti minus T infinity. Okay. So this is dimensionless temperature. You can see that the maximum temperature difference that can be is Ti minus T infinity. So at time equals 0, you will have theta star equals 1. And when it's completely cooled off, then T will be equal to T infinity, so it will be 0. So theta star will be between 0 and 1. Okay. Dimensionless spatial coordinate, we define x star is equal to x by L. L where is not full thickness, it's half thickness of the plate. It's not that. Right. So you can see we defined this x equals 0 at midplane minus L plus L. So L is half thickness. Then we define dimensionless time. We have already done that. So Fourier number is your dimensionless time, which is alpha T by L square. Again, L for this geometry is just plate thickness. If it's some different geometry, but still you could analyze in 1D heat transfer, you can take it as characteristic length. Okay. So now we'll non-dimensionalize our equation. So to start with, you have this equation here, del 2t by del x square. So let's write. So you have equals 1 by alpha. Okay. So now we know that theta star. So we'll just use the definitions here. These three things. So I'll just rewrite it again. So theta star we said is equal to t minus t infinity by ti minus t infinity, and x star we said is equal to x by L, and t star is equal to Fourier number, which is equal to alpha t by L square. Okay. Yeah. So so this term here, or let's start from right side. So we can do it here, and then we'll substitute. So del t by del t. Okay. So del t we can write as del, if you differentiate this, you will get ti minus t infinity. This term will come here, and then you differentiate both sides. So del theta star will be equal to del t. So this will be just this. Similarly, del t, if you find from here, it should be L squared t star by alpha. So L squared by alpha. Okay, that is fine. So we can maybe take alpha. Okay, so we can move this alpha from here to. Okay. So now we have to look at this side. So del 2t by del x square should be equal to the on the top. You will have the same thing, ti minus t infinity del theta is del 2 theta star, right? It's del 2. So recall that the operator over here is the second order operators. This del 2 by del x squared. Okay. So now x squared you have to write as L squared, L squared x star squared. Okay. So now all we have to do is equate these two and multiply this after multiplying this by 1 by alpha. Okay. So based on that, what we can write del 2t by del x square, and when you equate it, you will see that this and this term will also cancel out. This and this will cancel out, right? So let us first write this side. So this and this are going to cancel out. So only you will have left over as del 2 theta star by del x star square, right? Because this cancels with this will cancel with this. Okay. On the right side, you have to multiply this by 1 by alpha. So alpha will vanish. So we'll have just del theta star, del theta star, right? Now that this is the equation we have to solve. Now we have to also look at the boundary condition and initial conditions, right? So first of all, if you look at the initial condition, what was your initial condition? Tx0 equals Ti. Okay, so Tx0 equals Ti. Okay, yeah. So what you can do about it? Yeah. So this would mean that theta star at any x star, yeah, 0 should be what? Yeah. So if t is Ti, then theta star is what? Ti minus t infinity, so that is equal to 1. Okay. The second one is your mid-plane symmetry. So del t by del x at x equals 0 is 0. So for this, what we can do is del t by del x we know is del theta star, by del x star, and then you will have multiplication of this term and then L, right? So L will be here, Ti minus t infinity, but everything has to be 0, so those constants don't matter. So this is at x star equals 0, that should be equal to 0. Okay. So now third boundary condition you had as the at the surface you have conduction is equal to convection, so that is minus k del T by del x at x equals L is equal to h T at L and at any time T, but L means that you are talking about surface, or even minus L will have the similar thing, right? Okay. So for this part, again, this thing we know, minus k, this would be ti minus t infinity. From here we know that this thing will go here, and then we'll do the differentiation. So this will be ti minus t infinity dou theta, and this will be L. So you'll have L here. So by dou x star, and x equals L essentially means x star is equal to 1. Okay. This side will remain as it is. So now what we can do is we can let's do it in next line. This minus t infinity. Okay. So now what we can write is del theta. Actually, this will be theta star. Del theta star by del x star at x star equals L. This should be equal to, now you take it there, minus h L by k t L t minus t infinity by ti minus t infinity. This looks like your theta star. So this is your Biot number. So minus Biot number. Then you have theta star, and for x equals L, that would mean x star equals 1, and at any time t, that would mean at time equals t star, right? So so this becomes your boundary condition. This is equal to this. So with all these things, you should be, it's possible to solve this differential equation, and the solution comes actually in what we do is essentially, I'm not going to go into detail of the solution, but the solution is in the form of infinite series of product of two functions, gt and fx. Yeah, gt and fx, and there is a way to solve. So the time dependence is exponential, and you can roughly relate to it because it's first order differential equation, and then you try to integrate, you will get the logarithmic somewhere, and from there it becomes exponential. And this is the second order differential. So if you so this comes as trigonometric function. So this is of the form. So for Fourier number greater than 0.2, this series solution can only first term is important. Other terms are the sum of other terms are negligible. So you just take the first term. So only this is valid only if your Fourier number is greater than 0.2. So you cannot, using this equation, you cannot predict the temperature inside the body for a very short period of time. Fourier number is your dimensionless time. Okay, but for Fourier number greater than 0.2, this is a relatively simple equation that can be used to find theta star, and hence temperature profile within the body. Okay, so you can see this term, as I said earlier, is function of time. This term is function of space, and then C1 you can calculate from here, where zeta is given by you can see that this equation will have multiple solutions. So positive roots of this equation is taken as zeta. So only you take zeta 1, and then from there you can calculate C1. So these things are tabulated. So what you have to do is you have to first calculate Biot number. In the reference book, you will find that for the Biot number, you can find what is your zeta 1. And once you know zeta 1, and in fact the same table also gives you C1. Okay. So from there you will know C1, zeta 1, and all those things. So once you substitute that, you will know theta star. Okay. So this is how you solve it. In this type of problem, you start with by calculating Biot number. Then you find your constants, and then you substitute those constants here, and then you find the temperature. Okay. There may be problems where you may have to find for a given temperature what will be the time or what will be the location. That kind of problem may also be there. But to do anything, you have to first find Biot number, and then you move that way. Okay. So we saw that this is function of two product of two functions. Now in this equation, if you substitute x star equals 0, that would mean x equals 0. So x equals 0 was our midplane, right? This was x equals 0 or x star equals 0. So if you do that, then cos 0 is 1. So this will give you the C1 exponential of this term. So what it gives you is essentially how does the mid-plane temperature vary with time. Okay. So this gives you the mid-plane temperature. So if you call this mid-plane temperature as theta naught star, because it exactly doesn't give you the temperature, it gives you T of mid-plane at x equals 0 minus T infinity by Ti minus T infinity, right? This is what theta naught star is. So from here you can calculate mid-plane temperature. So anyway, so dimensionless mid-plane dimensionless temperature, if you know, then you can see that this term is essentially same as this term here. So you can write theta star as a function of mid-plane temperature, and then at any location, if you know, you can calculate the temperature. Okay. Yeah. Okay. So for fixed time, at you can see that the temperature profile will be in the body will be cosine. Okay. So once we know temperature profile, we can calculate other things. For example, here it's given from energy balance. You can similarly what we did for thermally thin body, now we can do the same thing for thermally thick body. I'll not go through math more. We have done this for thermally thin, so it's just integration you have to do again, and the function form is again similar to what we see earlier. Okay. So this gives you from here you can actually you can find how much heat has been transferred at a given time. Again, this is function of only mid-plane temperature, because you are talking about over the volume how much heat has been extracted by the liquid or gas. Okay. So once we have this solution, you can look at the other application of this solution. For example, we use mid-plane symmetry as one of our boundary condition. So since the mid-plane is symmetric, so half solution again should apply for your insulation. If you just solve it from 0 to L, then this is equivalent to having this as insulating surface. Okay. Yeah. So you can solve for a surface which goes from 0 to L, and then you have insulation here. So if this is insulation, then also you can use the same equation. Okay. We have seen this thing before. The second aspect is the sudden change in surface temperature. So suddenly, it was at Ti, and suddenly if you change the surface temperature to some Ti dash, or some Ti to T, then what that situation is essentially equivalent to H equals infinity. And for that condition, you can say Biot number is equal to infinity, because bio is equal to H L by K. Sudden change in temperature is almost equivalent to infinite heat transfer at the surface. So you can take H as infinity. Okay. So for Biot number infinity, we already know this term. From the table you can find. So this gives you zeta squared. So you already so this will be your zeta squared, and this will be your this is your cos zeta x. Okay, so this is zeta 1 squared, and this is zeta 1. Okay, so for Biot number, that's how these values are tabulated. So it will give you Biot number, and it will give you zeta 1, and it will give you C1, and so on. So this is your C1, this is zeta 1, this is zeta 1 squared. Okay, so for those conditions, you can just calculate what should be your temperature profile. Okay, so with that, let's do a simple problem. based on the concept that we just discussed. So the surface temperature of this 200 thick stainless steel slab is suddenly changed from 1000 Kelvin to 273 Kelvin. What is the temperature at 50 distance from the surface of the slab? So let us say you have a slab that is 200 thick. Yeah. So what we need to know is this is 100 This is 100 so from here to here 50 So what is the temperature at this location? This is what we want to know. Here T is equal to 1. Okay. And we want to know that after 600 seconds. So what you already are given the equation. So since you know this distance 50 so from there you can calculate x star. And theta naught you can calculate because you know the time. So this will be alpha t by L squared. Since you know the time, so you can calculate this Fourier number, and so from there you can calculate theta naught. So you have to calculate theta star. So you have to spend 2-3 minutes to do the calculation to go through it, so that you know you get confidence of how to solve such problems. Okay. So with that, this is end of end of lecture 17. We have still little bit content left for conduction, maybe half lecture or so, and then we'll start we'll start convection. Yeah, thank you for your attention. We'll see you in the next lecture. Okay.